Have you ever wondered what it would feel like to truly understand the place you call home? Not just your city or your country, but your cosmic address in the universe itself? Tonight, you are about to drift through one of the most beautiful mysteries in existence, the Milky Way, our galaxy. A vast spiral of light turning silently through space for over 13 billion years, carrying within it secrets that reach back to the very beginning of time. Most of us move through life without thinking about the incredible motion happening all around us. Right now, as you rest, you are traveling through space at over 800,000 kilometers per hour, swept along by a solar system that orbits the galactic center in a journey so vast it takes 225 million years to complete just once. The stars above you are not fixed. They are drifting, colliding, being born and dying in cycles older than memory itself. And beneath the beauty of that glowing band stretched across the night sky lies 100 secrets. Mysteries about rogue stars flung into darkness, ancient collisions that shaped our home, invisible forces that hold everything together, and remnants so old they remember a universe still learning to exist. Tonight, you will hear these secrets, one by one, gently woven into a story meant to ease your mind and carry you softly towards sleep. You will discover things that may surprise you, inspire quiet wonder, or simply let your thoughts float among the stars until they dissolve into rest. Before we begin, if you find peace in these cosmic journeys, please take a moment to like and subscribe. It helps others discover this little corner of the universe too, one sleepy explorer at a time. And now, let the stars guide you gently into stillness. Welcome to Sleepy Science Stories. The Milky Way stretches across the cosmos as both home and mystery. When you step outside on a clear night, away from the glow of cities, you might see a faint band of light arching overhead. That pale river is our galaxy seen from within. Billions of stars so distant, they blend together into a soft, luminous haze. But what you see is only the smallest glimpse. The galaxy extends in all directions, above and below, forward and back, a vast three-dimensional structure that holds everything you have ever known. It is older than almost anything we can imagine, yet it is not finished. It is both stable and changing, both ordered and chaotic. And tonight, we will wander through its depths together, gently, allowing each revelation to arrive like a soft breath in the dark. The Milky Way has already merged with other galaxies, and it will again. Our galaxy may seem like a steady home, yet it is forged from the remnants of others. Across billions of years, the Milky Way has pulled in smaller galaxies, drawing them close, tearing them apart, and spreading their stars into tidal streams that coil around the disk. One such victim, the Sagittarius dwarf galaxy, is being torn to pieces as we speak, and far beyond in the night sky, Andromeda drifts steadily nearer. In roughly 4.5 billion years, the two immense spirals will collide in a cosmic embrace. Stars will almost never strike one another, but the shapes of both galaxies will transform, folding into something new, vast and silent. Even galaxies are not forever. They shift, they merge, and they are reborn. These collisions happen slowly, unfolding over hundreds of millions of years. If you could watch from afar, time-lapse across eons, you would see the two galaxies approach like dancers. First, their outer edges would touch, distorting each other's shapes. Spiral arms would stretch and twist. Stars would be pulled into long arcs, tidal tails reaching out into space. Then, the cores would pass through each other, not colliding but interpenetrating, their stars mingling but rarely touching. The galaxies would separate briefly, then swing back together again, drawn by gravity's patient grip. With each pass, they would lose energy, moving slower, drawing closer. Eventually, they would settle into a single merged form, no longer two spirals but one elliptical mass, their identities lost in union. The process is gentle on the scale of individual stars, but dramatic on the scale of galaxies. It is both destruction and creation, an ending and a beginning. Some stars within the Milky Way are older than the Milky Way itself. Not every star here was born in this place. Some halo stars, ancient, metal poor, and travelling along tilted paths, seem to have formed even before the Milky Way had fully assembled. Astronomers think these stars may have come from smaller early galaxies that joined with ours billions of years ago. Their chemical makeup shows almost no heavy elements, suggesting they ignited shortly after the Big Bang. They drift slowly, high above the main disk, like ancient witnesses from a time before spirals, before structure. In their light, we glimpse a universe that was younger, stranger, and still becoming what it is now. These ancient stars are called Population 3, or the earliest population, 2 stars. They were born in a universe that contained almost no elements heavier than lithium. Everything else, the carbon, oxygen, iron and silicon that make up planets and life, had not yet been forged. These stars burned with primordial fuel, pure hydrogen and helium, the leftover ingredients from the Big Bang itself. Some of them still shine today, faint and red, their nuclear fires burning low after billions of years. Others have long since died, leaving behind white dwarfs or neutron stars, silent remnants of the first stellar generation. When we study these stars, we are looking back to the dawn of star formation, to a time when the universe was dark except for the first glimmers of light breaking through the cosmic fog. Our solar system circles the center of the Milky Way at over 828,000 kilometers per hour. That is more than 230 kilometers every second, and yet it takes roughly 225 million years to complete a single orbit around the galaxy. This journey is called a galactic year. In Earth time, we have only travelled around the Milky Way about 20 times since our solar system formed. When the first dinosaurs walked the Earth, we were elsewhere in the galaxy entirely. The stars we see tonight were not always our neighbours, and they will not remain so. Everything moves, quietly, steadily, endlessly. Even as we rest, the Earth spins. The Moon orbits, and the entire solar system sweeps onward through a galaxy in constant motion. Think about what a galactic year means for life on Earth. 225 million years ago, during the last time we were at this position in the galaxy, the continents were arranged differently. The supercontinent Pangaea was beginning to form. The first dinosaurs had not yet appeared. The dominant life forms were amphibians and early reptiles. Since then, solar system has travelled a quarter of the way around the galaxy, sweeping through different stellar neighbourhoods, passing through spiral arms, encountering different densities of dust and gas. The night sky looked different then. Different stars were visible, different constellations filled the heavens. And 225 million years from now, when we return to this spot again, Earth will be unrecognisable. The continents will have shifted, species will have risen and fallen, and new stars will light the night. The galaxy is still growing. Though the Milky Way is ancient, it is not complete. Even now it continues to gather matter. Gas from intergalactic space, stars from swallowed dwarf galaxies, and currents of dark matter that nourish its halo. It grows not as a living organism, but as a gravitational structure deepening over time. Some of this growth occurs quietly through drifting clouds. Other times, it arrives violently as smaller galaxies are ripped apart and their stars flung across the sky. The galaxy you inhabit today is not the same one that existed during the age of dinosaurs, and the one your far descendants might know could be larger still, woven from the ruins of 1,000 smaller worlds. Growth is not always peaceful. When a small galaxy falls into the Milky Way, the encounter is violent. The intruder is stretched by tidal forces, its shape distorted, its stars pulled into long streams. Some stars are captured into the halo, others are flung outward, ejected into intergalactic space. The gas within the smaller galaxy is compressed, triggering bursts of star formation. For a brief time, the collision zone glows with the light of newborn stars. Then, as the gas is consumed or dispersed, the burst fades. What remains is a stellar stream, a river of stars marking the path of the doomed galaxy. These streams can persist for billions of years, slowly mixing into the halo, gradually erasing the memory of the galaxy that once was. We do not know how many arms the Milky Way has. It seems like something we ought to know. How many arms spiral outward from the center of our own galaxy? Yet from our location deep within the disk, it is difficult to perceive the entire structure. Dust clouds hide distant regions. Stars blend into one another. For decades, astronomers thought there were 4 major spiral arms. More recent studies suggested perhaps fewer, or that the arms twist and divide in ways more intricate than imagined. Some dissolve into fragments, others curve unexpectedly. The Milky Way may not be a tidy pinwheel at all, but a dynamic, layered swirl of stars shaped by forces we still do not entirely grasp. Part of the difficulty lies in perspective. Imagine trying to draw a map of a city while standing at street level, surrounded by buildings. You can see the structures nearby, but distant neighborhoods are hidden. The overall layout is invisible. This is our situation within the Milky Way. We can map the stars near the Sun with great precision. But farther out, especially toward the opposite side of the galaxy, the view becomes murky. Dust clouds in the disk block our view. We must rely on indirect methods, radio observations of gas clouds, infrared maps of cool stars, and careful measurements of stellar distances. Each new survey reveals more complexity, more substructure, more hints that the galaxy is not as simple as we once believed. Rogue stars are ejected from the core. Most stars glide peacefully through the galaxy, but a rare few are launched outward at incredible speeds, fast enough to leave the Milky Way forever. These are hypervelocity stars. Some are the survivors of binary systems torn apart by the supermassive black hole at the galactic center. One star is consumed and vanishes. The other is flung outward, hurled into darkness at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like luminous comets with no destination. They remind us that even within a galaxy held by gravity, there are moments of fierce release, silent expulsions that send stars racing into intergalactic void. Hypervelocity stars are rare, but they are not unique. Astronomers have identified dozens of them, scattered across the sky, all moving outward at tremendous speeds. Some are blue and hot, massive stars still burning brightly. Others are smaller, older, cooler. Their paths, traced backward through time, often point toward the galactic center, confirming their violent origin. A few may have been ejected by other means, perhaps flung out during the collision with a dwarf galaxy, or accelerated by interactions with massive star clusters. Whatever their source, they are exiles, stars that will never return. They will drift through intergalactic space for billions of years, slowly fading, eventually dying alone in the dark between galaxies. The Milky Way and Andromeda are racing toward collision. High above the horizon, the Andromeda galaxy appears as a faint smudge to the unaided eye, a spiral much like ours, resting over 2 million light-years away. Yet it is approaching us steadily. In approximately 4.5 billion years, the Milky Way and Andromeda will collide. It will not be violent in the way you might expect. Stars are spaced too distantly to crash head-on, but their gravity will distort both galaxies into long, stretching arcs. Tidal tails will spiral outward. Black holes may circle each other. And after billions of years, the two galaxies will merge into a single, larger system. It will be a slow, graceful waltz, the future of our home written across the heavens. When the merger is complete, the resulting galaxy will be different from either of its parents. It will likely be an elliptical galaxy, a smooth, featureless ball of stars rather than a spiral. The ordered rotation of the disks will be lost, replaced by random orbits. Stars will move in all directions, their paths dictated by the collective gravity of the merged mass. The new galaxy will be larger, containing perhaps 1 trillion stars, one of the largest in the local group. It will be older, quieter, more settled. Star formation will slow as the gas is consumed or dispersed. Over billions of years, the galaxy will age, its stars growing redder, dimmer, cooler. It will become a monument to what once was, 2 great spirals now united in stillness. Some stars orbit backward. Most stars in the Milky Way circle the center in the same general direction, yet not all obey the pattern. Some stars, particularly in the outer halo, move in retrograde, orbiting opposite to the galaxy's main spin. These stars likely arrived from somewhere else, born in dwarf galaxies that were later absorbed. Their reversed motion is a subtle signature of their foreign origin. It is as though the galaxy holds old memories in its movement. Stories of ancient mergers and cosmic meetings preserved not in light, but in the slow, deliberate turning of stars against the current. Retrograde stars are clues to the galaxy's past. By mapping their orbits and measuring their chemical compositions, astronomers can reconstruct the history of past mergers. Each captured dwarf galaxy leaves a unique signature. Its stars share similar orbits, similar speeds, similar chemical fingerprints. By grouping stars with matching characteristics, astronomers can identify which stars came from which galaxy. They can estimate when the merger occurred, how large the intruder was, and how it has since been dispersed. The retrograde stars are messengers from the past, carrying information about events that happened billions of years ago, events that shaped the galaxy we see today. The Milky Way may have consumed dozens of dwarf galaxies. Over billions of years, the Milky Way has not grown alone. It has devoured. Small galaxies, faint glowing neighbours, have drifted too close, been captured by its gravity and slowly torn apart. Their stars are now part of our halo, our disk or stellar streams. Astronomers have traced several of these mergers by studying stellar motion and chemistry. One particularly massive event, the Gaia-Enceladus merger, added countless stars and may have reshaped the early form of the galaxy. The Milky Way is not a pristine spiral, it is a composite, built from quiet collisions, stitched together from the ruins of many smaller realms. The Gaia-Enceladus merger was significant. It occurred roughly 10 billion years ago, early in the galaxy's history, when the Milky Way was still young and less massive. The intruding galaxy was large for a dwarf, perhaps a quarter the mass of the Milky Way at the time. The collision was violent. It disrupted the early disk, thickening it, heating it, and scattering stars into the halo. It may have triggered intense star formation, igniting a burst of new stars throughout the galaxy. The merger also deposited a large amount of dark matter into the halo, contributing to the galaxy's overall mass. Today, the remnants of Gaia-Enceladus are scattered throughout the galaxy. Its stars are mixed with ours, indistinguishable except for their chemical signatures and their orbits. The merger is over, but its effects persist. The chemical makeup of stars reveals their origin. Every star carries a unique chemical signature, a pattern of elements imprinted at its birth. By studying these signatures, astronomers can trace a star's past. Some stars are rich in heavy elements like iron and calcium, suggesting they formed in dense, metal-rich regions. Others are nearly pure hydrogen and helium, born when the universe was still very young. These differences allow scientists to separate stars into populations, identifying which were born locally and which were adopted from elsewhere. The galaxy remembers its history through chemistry. This technique is called stellar archaeology. By analysing the light from stars, astronomers can determine which elements are present and in what quantities. They can measure the abundance of iron, magnesium, carbon, oxygen, and dozens of other elements. Each element tells part of the story. Iron is produced in supernovae, the explosive deaths of massive stars. Carbon comes from aging red giants, stars shedding their outer layers into space. Oxygen is forged in the cores of massive stars. By comparing the abundances of different elements, astronomers can deduce where and when a star was born. Stars from dwarf galaxies often have different chemical patterns than stars born in the Milky Way. They may have more magnesium relative to iron, or less oxygen relative to carbon. These subtle differences are fingerprints, unique markers that reveal a star's true origin. Dark matter makes up most of the galaxy's mass. The stars we see, the dust we detect, the gas we measure, together they account for only a small fraction of the Milky Way's total mass. The rest is dark matter, invisible to all forms of light. We know it exists because its gravity shapes the rotation of the galaxy and holds it together. Without dark matter, the outer stars would fly away. The spiral would unravel, yet we cannot see it, touch it, or measure it directly. It surrounds the galaxy in a vast halo, silent and unknowable, the hidden framework upon which everything visible rests. Dark matter is one of the greatest mysteries in science. We do not know what it is made of. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. Dozens of experiments have tried to detect it directly, searching for dark matter particles passing through detectors deep underground. So far, none have succeeded. Dark matter remains elusive, a substance that dominates the universe yet refuses to reveal itself. Some theories suggest it is made of exotic particles, remnants from the Big Bang, perhaps called WIMPs, weakly interacting massive particles. Others propose it is axions, tiny particles that barely interact with anything. Still others wonder if dark matter is not a particle at all, but something stranger, a modification of gravity itself at large scales. The answer remains unknown. The galactic disk is not flat. For decades, astronomers assumed the Milky Way's disk was a neat, flat plane. But observations reveal something different. The disk is warped. Its edges curl upward on one side and downward on the other, like a bent vinyl record. This warp may be caused by gravitational tugs from nearby dwarf galaxies, or from the motion of dark matter currents flowing past. Whatever the cause, it means the Milky Way is not the tidy structure we once imagined. It is alive, bending, responding to forces we are only beginning to understand. The warp extends for thousands of light years, gradually twisting the disk out of alignment. Near the Sun, the disk is relatively flat, but farther out, toward the edges, the deviation becomes noticeable. In some directions, the disk tilts upward by several thousand light years. In others, it dips downward. The warp is not static. It changes over time, precessing like a wobbling top, rotating slowly around the galactic center. This motion suggests the warp is a wave, a ripple in the disk caused by something pulling on it. The Magellanic Clouds are prime suspects. These two small galaxies orbit the Milky Way, and their gravity may be tugging on the disk, creating the warp we observe. If so, the warp is evidence of an ongoing interaction, a reminder that the Milky Way is not isolated but influenced by its neighbours. The galactic centre is shrouded in dust. At the heart of the Milky Way lies a dense and crowded region, packed with stars, gas and radiation, yet we cannot see it in visible light. Dust clouds, thick and pervasive, block our view. To peer into the centre, astronomers use infrared and radio telescopes, which can penetrate the veil. There, they find a supermassive black hole surrounded by swirling matter and ancient stars. It is a place of extremes. a hidden heart pulsing at the core of our galaxy, invisible yet undeniably powerful. The dust that blocks our view is not ordinary dust. It is composed of tiny grains, smaller than particles of smoke, made of carbon, silicates, and ice. These grains form in the outer atmospheres of aging stars, condensing from gas as the stars shed their layers. The grains are then dispersed into space by stellar winds and supernova explosions. Over time, they accumulate in the disk, especially in dense regions where star formation occurs. The dust absorbs and scatters visible light, making distant stars appear dimmer and redder. But it is transparent to infrared and radio waves. These longer wavelengths pass through the dust almost unimpeded, allowing astronomers to see what lies beyond. Without infrared and radio astronomy, the galactic center would remain forever hidden, a mystery at the heart of our home. The supermassive black hole is named Sagittarius, a star. At the exact center of the Milky Way sits a black hole with a mass of about 4 million suns. This is Sagittarius, a star, a monstrous presence so dense that nothing, not even light, can escape its pull once past the event horizon. It does not feed constantly. Most of the time, it sits quiet, occasionally flaring as stray gas or unlucky stars wander too close. Orbiting this black hole are stars moving at incredible speeds, their paths dictated entirely by its gravity. Studying these orbits has confirmed not just the black hole's existence, but its size and power. Some of these orbiting stars move at a significant fraction of the speed of light. One star, designated Stu, completes an orbit in just 16 years, swinging close to the black hole at speeds exceeding 5,000 kilometers per second. At closest approach, it passes within 17 light hours of the event horizon, experiencing gravitational forces so intense that time itself slows relative to observers farther away. By tracking Stu and other stars over decades, astronomers have mapped their orbits with extraordinary precision. These orbits follow the predictions of general relativity, Einstein's theory of gravity. They curve and precess in exactly the way predicted for objects moving in the intense gravitational field of a black hole. This is one of the strongest pieces of evidence we have for the existence of black holes and for the validity of Einstein's theory in extreme conditions. The central bulge holds billions of older stars. Surrounding the black hole is the galactic bulge, a dense, swollen region packed with older, reddish stars. These stars formed early in the galaxy's history and have been orbiting the center ever since. The bulge is not as flat as the disk. It is roughly spherical, or perhaps slightly elongated, a glowing core visible from afar. Within this crowded heart, stars pass each other more frequently than in the disk. Collisions are still rare, but encounters are not. It is a dense, ancient neighborhood, quiet and stable, filled with the slow motion of aging stars. The bulge may also contain a bar, a rectangular structure of stars extending outward from the center. Observations suggest the Milky Way is a barred spiral galaxy, meaning its central region is elongated rather than round. The bar rotates as a solid structure, its stars moving together in lockstep. This bar may play a role in funneling gas toward the center, feeding star formation and potentially feeding the central black hole. Bars are common in spiral galaxies, appearing in roughly 2/3 of all spirals observed. They form through gravitational instabilities in the disk, regions where stars naturally clump together. Once formed, bars can persist for billions of years, slowly reshaping the galaxy from within. Spiral arms are regions of higher star formation. The Milky Way's spiral arms are not solid structures. They are not chains of stars moving together. Instead, they are density waves, regions where gas and dust pile up, compress and trigger new star formation. As material flows into an arm, it slows, bunches together, and ignites. Bright young stars are born, lighting up the arm in blue and white. Over time, these stars drift away, but new ones form to replace them. The arms themselves persist, not because the same stars stay there, but because the conditions for birth remain. They are not places, they are events. Think of spiral arms as traffic jams in space. On a highway, a traffic jam is not a fixed thing. Cars enter the jam from behind, slow down, and then exit at the front. The jam itself stays in roughly the same location, even though the individual cars are always changing. Spiral arms work the same way. Gas and stars flow into the arm, slow down due to the increased density, and then flow out the other side. The arm remains because the density wave persists, a pattern in the disk that shapes the flow of material. These density waves may be caused by gravitational interactions with other galaxies, by the rotation of the bar, or by instabilities within the disk itself. They are self-sustaining patterns, waves that propagate through the galaxy, sculpting its structure. Star formation happens in molecular clouds. New stars do not appear randomly. They are born in vast clouds of molecular gas, primarily hydrogen, cooled to just a few degrees above absolute zero. These clouds are dense and dark, shielded from outside light. Within them, gravity pulls material together. Clumps form, collapse, and heat up. When the core becomes hot and dense enough, nuclear fusion begins. A star ignites. This process can take millions of years. The clouds themselves are enormous, stretching across dozens or even hundreds of light years, and within a single cloud, hundreds of stars may be born. Molecular clouds are the coldest places in the galaxy. Inside them, temperatures can drop to just 10 or 20 degrees above absolute zero. At these temperatures, hydrogen molecules can survive without being torn apart by radiation. The cold also allows the gas to collapse more easily. Warm gas resists compression. Cold gas does not. Gravity can pull cold gas into denser and denser clumps until star formation begins. These clouds are opaque to visible light. From the outside, they appear as dark patches against the glow of the Milky Way. But inside, they are bustling with activity. Stars are forming. Jets of gas shoot out from newborns. Shock waves ripple through the cloud. It is a chaotic, creative environment, the birthplace of everything that follows. The Orion Nebula is a nearby stellar nursery. Roughly 1,300 light-years away, the Orion Nebula glows in the night sky as a faint smudge visible even to the naked eye. It is one of the closest and brightest regions of active star formation we can observe. Within its glowing gas and dust, young stars are forming, some only a few 100,000 years old. The nebula glows with the light of hot, newborn stars, their radiation ionizing the surrounding gas and making it shine. It is a window into the process that gave birth to our own sun billions of years ago. The Orion Nebula is part of a much larger complex of molecular clouds. The entire Orion constellation is a hotbed of star formation, filled with dark clouds, glowing nebulae, and young star clusters. The brightest stars in Orion, the ones that form the Hunter's belt and shoulders, are all young, hot, and massive, born within the last few million years. They will not last long. Within 10 or 20 million years, they will explode as supernovae, scattering their remains and triggering new waves of star formation. The Orion region is a laboratory for studying stellar birth and death, a place where we can watch the galaxy renewing itself. Massive stars live fast and die young. The most massive stars in the galaxy burn incredibly hot and bright. They consume their fuel at a staggering rate, fusing hydrogen into heavier elements within just a few million years. When their cores can no longer sustain fusion, they collapse and explode in supernovae, brilliant bursts of light that can briefly outshine entire galaxies. These explosions scatter heavy elements into space, enriching the gas that will form the next generation of stars. Massive stars are rare, spectacular, and short-lived. They shape the galaxy through their deaths as much as their lives. A star with 10 times the mass of the Sun might live for only 20 million years. A star with 50 times the Sun's mass might last just a few million. Compare this to the Sun, which will shine for about 10 billion years in total. Massive stars burn through their fuel so quickly because their cores are much hotter. The rate of nuclear fusion depends strongly on temperature. A star twice as hot fuses hydrogen thousands of times faster. This rapid fusion produces enormous amounts of energy, making massive stars incredibly luminous. But it also means they exhaust their fuel quickly. They rush through their lives, burning bright and fast, then collapsing in violent death. Red dwarfs are the galaxy's longest-lived stars. At the opposite end of the spectrum are red dwarfs, small, cool stars that burn their fuel slowly and steadily. These stars can live for trillions of years, far longer than the current age of the universe. They are the most common stars in the galaxy, yet they are so faint that none are visible to the naked eye. Red dwarfs will outlast almost everything else. Long after stars like the Sun have died, red dwarfs will still be shining, faint embers in a cooling galaxy. Red dwarfs are small, typically less than half the mass of the Sun. Their cores are cooler and less dense than those of larger stars. Fusion proceeds slowly, releasing energy at a gentle pace. This slow burn means red dwarfs are incredibly efficient. They can fuse a much larger fraction of their hydrogen than larger stars can. Some red dwarfs may eventually fuse nearly all their hydrogen, converting almost their entire mass into helium. When they finally exhaust their fuel, they will simply fade away, cooling slowly into white dwarfs. No supernova, no dramatic explosion, just a quiet dimming, a star gently giving up its light. White dwarfs are stellar remnants. When stars like our Sun exhaust their fuel, they do not explode. Instead, they shed their outer layers gently, leaving behind a hot, dense core called a white dwarf. These remnants are roughly the size of Earth, but contain as much mass as the Sun. They no longer produce energy through fusion. Instead, they simply cool over billions of years, fading slowly from white to yellow to red, and eventually to black. White dwarfs are the most common stellar endpoint in the galaxy, quiet monuments to stars that once burned bright. A white dwarf is held up not by fusion or gas pressure, but by electron degeneracy pressure. This is a quantum mechanical effect that prevents electrons from being squeezed too closely together. In a white dwarf, electrons are packed so tightly that they resist further compression. This pressure balances gravity, keeping the white dwarf stable, but there is a limit. If a white dwarf gains too much mass, perhaps by pulling material from a companion star, it can exceed the Chandrasekhar limit, about 1.4 times the mass of the Sun. Beyond this limit, electron degeneracy pressure is no longer enough. The white dwarf collapses, triggering a runaway fusion reaction that destroys the star in a Type Ia supernova. These explosions are incredibly bright and remarkably consistent, making them useful as standard candles for measuring cosmic distances. Neutron stars are incredibly dense. When a massive star collapses in a supernova, its core can be crushed into an object so dense that protons and electrons merge into neutrons. This is a neutron star, a sphere only about 20 kilometers across, but containing more mass than the Sun. A teaspoon of neutron star material would weigh billions of tons. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like a lighthouse. These are pulsars, and their precise timing makes them among the most accurate clocks in the universe. Neutron stars are held up by neutron degeneracy pressure, similar to the electron degeneracy that supports white dwarfs but far stronger. The material inside a neutron star is unlike anything found on Earth. The outer crust may be solid, composed of iron nuclei embedded in a sea of electrons. Deeper in, the nuclei break apart into a soup of neutrons. At the very core, the The conditions are so extreme that we do not fully understand what happens. The density may be high enough to create exotic forms of matter, quark matter or strange matter, substances that exist nowhere else in the universe. Neutron stars are laboratories of extreme physics, places where our theories are pushed to their limits. Black holes form from the most massive stars. When the core of an extremely massive star collapses, not even neutron pressure can stop it. The core shrinks past the point of no return, forming a black hole. Around this singularity lies the event horizon, the boundary beyond which nothing can escape. Black holes do not emit light. They are detected only by their effects on nearby matter, their gravitational pull, or the radiation released by material falling into them. They are the universe's ultimate endpoint, silent voids where matter and even time behave in ways we struggle to comprehend. The event horizon is not a physical surface, it is simply a boundary in space-time. Outside the horizon, escape is possible. Inside, escape is not. Nothing that crosses the horizon can ever return. Even light travelling at the fastest possible speed cannot climb back out. To an outside observer, anything falling into a black hole appears to slow down as it approaches the horizon, its light becoming redder and dimmer until it fades from view. To the falling object, however, time proceeds normally. It crosses the horizon without noticing anything special, then continues falling toward the singularity at the centre. What happens at the singularity, where gravity becomes infinite and space-time itself breaks down, is unknown. Our current theories cannot describe it. The singularity is a place where physics ends. Some binary stars orbit very close together. Not all stars travel alone. Many exist in pairs, bound by gravity, orbiting a common centre of mass. Some binaries are widely separated, their orbits taking centuries to complete. Others are so close that their surfaces nearly touch. Material can flow from one star to the other, altering their evolution. In the most extreme cases, one star may consume its companion entirely. Binary systems are laboratories of stellar physics, revealing dynamics impossible in solitary stars. Close binaries can produce some of the most dramatic events in the galaxy. If one star swells into a red giant while its companion remains smaller, gas from the giant can spill over onto the companion. This mass transfer can be gentle or violent, steady or episodic. In some cases, the companion is a white dwarf or neutron star. When gas falls onto such a compact object, it heats up to millions of degrees, emitting X-rays and sometimes triggering explosions. These systems are X-ray binaries, some of the brightest X-ray sources in the sky. They flicker and flare, their brightness changing over hours or days as the accretion rate varies. They are cosmic lighthouses, beacons that reveal the presence of otherwise invisible, compact objects. Nova explosions occur in binary systems. In certain binary systems, a white dwarf pulls material from a companion star. This stolen gas accumulates on the white dwarf's surface, growing hotter and denser. Eventually, the pressure triggers a runaway fusion reaction. The surface erupts in a nova, a sudden burst of light that can briefly make the system thousands of times brighter. The white dwarf survives the explosion. Over time, it resumes stealing gas, and the process may repeat. Novae are not the deaths of stars. They are cycles of theft and eruption, quiet violence repeated over and over. Novae can recur multiple times. Some systems have been observed to undergo nova eruptions every few decades. Each time, the white dwarf steals enough gas to reach the critical density for fusion. The surface explodes, blowing off the accumulated material. Then the cycle begins again. These recurrent novae are like cosmic volcanoes, erupting periodically, each time releasing a burst of energy and enriching the surrounding space with newly fused elements. the white dwarf itself remains largely unchanged. It continues to orbit its companion, continues to steal gas, and continues to explode. It is a strange, persistent cycle, a star that dies and is reborn again and again. Supernova remnants enrich the interstellar medium. After a supernova explosion, the debris does not simply vanish. It expands outward in a glowing shell, a supernova remnant that can persist for thousands of years. This material is rich in heavy elements, carbon, oxygen, iron, gold, forged in the heart of the dying star. As the remnant spreads, it mixes with the surrounding gas, enriching it. Future generations of stars will inherit this material. Planets will form from it. Life may emerge. Every atom heavier than hydrogen or helium in your body was created in a star and scattered by a supernova. Supernova remnants are beautiful structures. They glow in multiple wavelengths, visible light, radio, X-rays, each revealing different aspects of the explosion. The outer shell is where the expanding debris crashes into the surrounding gas, creating a shock wave that heats the material to millions of degrees. This shock wave accelerates particles to near light speed, producing cosmic rays. Inside the shell, the ejecta are still cooling, glowing with the light of newly formed elements. Sometimes a pulsar or young neutron star sits at the center, spinning rapidly and injecting energy into the remnant. These remnants are laboratories for studying nucleosynthesis, the process by which elements are created, and for understanding how stars give back to the galaxy. The Crab Nebula is a famous supernova remnant. In the year 1054, Chinese astronomers recorded a new star so bright it was visible during the day. Today, we know it as the Crab Nebula, the expanding remains of a supernova explosion. At its center lies a rapidly spinning neutron star, pulsing 30 times per second. The nebula glows with its energy, a delicate web of gas and radiation. It is one of the most studied objects in the sky, a cosmic laboratory where we observe the aftermath of stellar death. The Crab pulsar is one of the few pulsars whose optical pulses can be seen with telescopes. Most pulsars are detected only in radio waves. The Crab pulses across the entire electromagnetic spectrum, from radio to gamma rays. This makes it an ideal target for studying pulsar physics. The pulsar is young, less than 1,000 years old, and it is still slowing down, losing rotational energy over time. This energy is pumped into the surrounding nebula, keeping it glowing brightly. Eventually, the pulsar will slow to the point where it is no longer detectable. The nebula will fade. But for now, the Crab remains a brilliant monument to a star that died nearly 1,000 years ago. Pulsars emit beams of radiation. Pulsars are neutron stars that spin rapidly, sometimes hundreds of times per second. As they rotate, they emit beams of radiation from their magnetic poles. If one of these beams sweeps across Earth, we detect a pulse, like a lighthouse flashing in the night. The timing of these pulses is extraordinarily precise, so much so that pulsars have been used as cosmic clocks. They are the remnants of massive stars, spinning relics that challenge our understanding of matter under extreme conditions. The fastest known pulsar spins over 700 times per second. This is near the theoretical limit for neutron stars. If they spun any faster, the centrifugal force would tear them apart. These millisecond pulsars are typically old neutron stars that have been spun up by accreting matter from a companion star. As gas falls onto the neutron star, it carries angular momentum, causing the star to spin faster and faster. Eventually, the accretion stops and the pulsar is left spinning at incredible speeds. These millisecond pulsars are incredibly stable. Their rotation rate changes by only a tiny fraction over years or decades. This stability makes them useful for testing general relativity, searching for gravitational waves, and even for navigation. Some scientists have proposed using pulsars as cosmic GPS beacons for spacecraft traveling through the galaxy. Magnetars have the strongest magnetic fields known. Among neutron stars, magnetars are the most extreme. Their magnetic fields are trillions of times stronger than Earth's, so powerful they distort the very atoms around them. Occasionally, a magnetar's crust fractures, releasing a burst of energy that can briefly outshine the entire galaxy in certain wavelengths. These outbursts are called starquakes. Magnetars are rare, violent, and poorly understood. They push the boundaries of physics, objects where reality bends under forces we can barely imagine. Magnetars are dangerous even from a distance. If a magnetar existed within 1,000 kilometers of Earth, its magnetic field would be strong enough to disrupt the molecular bonds in your body. Fortunately, the nearest known magnetar is several thousand light-years away. Magnetars are rare. Only about 30 have been identified in the entire Milky Way. They are young, typically less than 10,000 years old, and they fade over time. As they age, their magnetic fields weaken, and their outbursts become less frequent. Eventually, they may become ordinary pulsars, no longer distinguishable from their less extreme cousins. But during their youth, magnetars are among the most violent objects in the galaxy, unpredictable and powerful. Globular clusters orbit in the halo. Scattered throughout the halo of the Milky Way are globular clusters, dense spherical collections of hundreds of thousands of stars. These clusters are ancient, some over 12 billion years old, formed in the earliest epochs of the galaxy's history. The stars within them are tightly packed, sometimes only light weeks apart. Globular clusters do not follow the rotation of the disk. Instead, they orbit the galactic center on long elliptical paths, like satellites circling a planet. They are fossils of the early galaxy preserved in the halo. Inside a globular cluster, the sky would look very different. Instead of a few thousand stars visible to the naked eye, as we see from Earth, you might see hundreds of thousands or even millions of stars scattered across the sky. The brightest would be red giants, huge cool stars nearing the end of their lives. The cluster would glow with a soft reddish light, the combined light of all its aging stars. At the center, stars would be so close together that gravitational interactions would be common. Binary systems would form and break apart. Stars would occasionally collide, merging into blue stragglers, stars that appear younger than they should. The cluster would be a dynamic, crowded environment, very different from the sparse region around the Sun. Open clusters are younger and looser. Unlike globular clusters, open clusters are found in the disk. They contain fewer stars, typically a few hundred, and are much younger, often only a few million or 100 million years old. These clusters form together from the same molecular cloud, and for a time they stay grouped. But over tens or hundreds of millions of years, gravitational interactions pull them apart. The stars scatter into the disk, going their separate ways. Our Sun may have been born in an open cluster, but if so, its siblings have long since drifted away. Open clusters are stellar nurseries still in the process of dissolving. When you look at a young open cluster, you are seeing a snapshot of star formation. The stars are still surrounded by remnants of the molecular cloud from which they formed. Gas and dust linger. The brightest stars are massive and hot, burning blue and white. They light up the cluster, ionizing the surrounding gas and making it glow. These bright stars will not last long. Within a few million years, they will explode as supernovae, scattering the cluster and triggering new star formation nearby. The less massive stars will gradually drift apart, spreading through the disk. After a few 100 million years, the cluster will be gone, its stars dispersed, indistinguishable from the general population. The Pleiades is a well-known open cluster. Also called the Seven Sisters, the Pleiades is a bright, beautiful cluster visible to the naked eye. It lies about 440 light-years away and contains over 1,000 stars. The brightest few are blue and hot, young stars only about 100 million years old. The cluster is surrounded by faint nebulosity, wisps of gas reflecting the star's light. The Pleiades has been observed for millennia, mentioned in ancient texts and woven into myths across cultures. It is a reminder that even the sky we see is shared across human history. Many cultures have myths about the Pleiades. In Greek mythology, they are 7 sisters pursued by Orion the hunter. In Japan, they are Subaru, meaning united. The cluster appears on the flag and logo of Subaru automobiles. In Aboriginal Australian lore, the Pleiades are associated with the seasons and the timing of food gathering. The cluster rises in the evening sky at different times of year, marking seasonal changes. For ancient peoples, the stars were not just beautiful. They were a calendar, a guide, a connection to the cosmos. Even now, when we know the Pleiades are merely a cluster of young stars bound by gravity, they retain their cultural power, a link between science and story. Stars move through the galaxy in orbits. Every star in the Milky Way is in motion, following an orbit around the galactic center. These orbits are not circular. They are elliptical, tilted, and influenced by the gravity of countless other objects. Stars bob up and down through the disk as they travel, crossing the galactic plane every few tens of millions of years. Some wander farther from the center, others stay close. The galaxy is not static. It is a river of stars flowing in slow, overlapping currents. The sun's orbit is not a simple circle. It oscillates vertically, moving above and below the galactic plane in a slow wave. This vertical motion is caused by the gravitational pull of the disk itself. When the sun is above the plane, the disk's gravity pulls it back down. When it is below, the disk pulls it back up. The result is a gentle bobbing motion, up and down, with a period of about 60 million years. At the same time, the sun's distance from the galactic center varies slightly. Its orbit is slightly elliptical, bringing it closer to the center at some times and farther away at others. These variations are small, but they have consequences. As the sun moves through different regions of the galaxy, it encounters different densities of gas, dust, and stars. These encounters may affect the solar system in subtle ways, perturbing comets, altering the cosmic ray flux, or even influencing the rate of impacts on Earth. Our sun oscillates through the galactic plane. As the sun orbits the center of the galaxy, it does not stay perfectly within the disk. Instead, it moves up and down, crossing the galactic plane roughly every 30 million years. At the moment, we are slightly above the plane, drifting through a relatively sparse region. These oscillations may have consequences. Some researchers have speculated that passing through denser regions of the disk could disturb comets in the distant Oort cloud, potentially triggering impacts on Earth. The motion is subtle, but its effects ripple through the solar system. There is a controversial hypothesis that links these galactic oscillations to mass extinctions on Earth. The idea is that as the solar system passes through the disk, the increased density of matter disturbs the Oort cloud, sending comets hurtling toward the inner solar system. Some of these comets might collide with Earth, causing mass extinctions. The hypothesis suggests that extinctions occur periodically, roughly every 30 million years, matching the sun's crossing time. However, the evidence is weak. The extinction record does not show a clear periodicity, and the mechanism for disturbing comets is uncertain. Most scientists are skeptical, but the idea remains intriguing, a reminder that our motion through the galaxy might have unexpected consequences. Stellar streams trace ancient mergers. Wrapped around the Milky Way are long, thin streams of stars, stretched across thousands of light years. These are stellar streams, the remnants of dwarf galaxies or globular clusters that were torn apart by the Milky Way's gravity. As the smaller object orbits, tidal forces pull it into a line like taffy stretched thin. By mapping these streams, astronomers can reconstruct the history of the galaxy's growth, identifying which galaxies were consumed and when. The streams are faint, delicate, and beautiful, ghostly traces of ancient violence. Stellar streams are like cosmic breadcrumbs. They mark the path of a doomed galaxy or cluster as it orbits the Milky Way. By tracing the stream, astronomers can determine the orbit of the progenitor, how long ago it was disrupted, and how massive it was. Some streams have been followed for multiple loops around the galaxy. Others are so faint they have only recently been detected. The discovery of new streams is accelerating thanks to missions like Gaia, which can measure the positions and motions of billions of stars. Each new stream adds a piece to the puzzle, helping us understand how the Milky Way grew and what it consumed along the way. The Sagittarius stream is currently being disrupted. The Sagittarius dwarf galaxy is not just a historical curiosity, it is being torn apart right now. Its stars are spread out in a long stream that wraps around the Milky Way multiple times, like ribbons winding through the galaxy. This process has been ongoing for billions of years. Each time the dwarf galaxy passes through the disk, it loses more stars. Eventually, it will be completely shredded, its stars absorbed into the halo. We are witnessing galactic cannibalism in slow motion. The Sagittarius dwarf is one of the Milky Way's closest satellite galaxies. It lies on the far side of the galactic center, hidden by dust and stars. It was not discovered until 1994, despite being so close. Its stars are faint and spread out, making it difficult to distinguish from the general background. But once identified, its stream was traced across the sky. The stream loops around the galaxy at least twice, possibly 3 or 4 times. The oldest parts of the stream have been dispersed by tidal forces and by interactions with the disk. The youngest parts are still relatively intact, trailing behind the remnant core of the dwarf. Over time, even these will disperse. The Sagittarius dwarf is dying, slowly dissolving into the Milky Way. The large and small Magellanic Clouds are satellite galaxies. Visible from the southern hemisphere, the Magellanic Clouds appear as 2 bright, fuzzy patches in the night sky. They are not stars, but small galaxies orbiting the Milky Way. The large Magellanic Cloud contains roughly 30 billion stars. The small Magellanic Cloud has a few billion. They are close enough that their gravity affects the Milky Way, and the Milky Way affects them in turn. Over time, they too may be absorbed. For now, they remain companions, irregular dwarfs trailing in our gravitational wake. The Magellanic Clouds are irregular galaxies. Unlike the Milky Way and Andromeda, which are spirals, the Magellanic Clouds have no clear structure. They are lumpy, chaotic, filled with star-forming regions and young star clusters. This irregularity may be the result of tidal interactions with the Milky Way. The Milky Way's gravity has distorted their shapes, pulled out streams of stars, and triggered bursts of star formation. The clouds are laboratories for studying star formation in low metallicity environments. Their stars are less enriched in heavy elements than stars in the Milky Way, making them more similar to galaxies in the early universe. The Magellanic Stream is a trail of gas. Stretching behind the Magellanic Clouds is a vast stream of hydrogen gas, pulled from the clouds by the Milky Way's gravity. This stream extends for over 500,000 light-years, a tenuous ribbon marking the path of the clouds through space. It is evidence of the ongoing interaction between the Milky Way and its satellites. Gas is being stripped away, and eventually it will fall into the disk, fueling new star formation. The galaxy grows not just by consuming stars, but by stealing gas. The Magellanic Stream was discovered in the 1970s through radio observations. It is invisible to the eye, invisible to optical telescopes. but it glows in radio waves emitted by hydrogen atoms. The stream is not uniform. It has clumps and gaps, regions where the gas is denser and regions where it is thinner. These variations may be caused by interactions with the Milky Way's halo or by turbulence within the stream itself. The stream is also trailing a leading arm, a stream of gas ahead of the cloud's current position. Together, the stream and the leading arm trace the orbit of the Magellanic Clouds around the Milky Way. They are a map of motion, a record of the cloud's journey through the halo. Interstellar dust obscures starlight. Between the stars lies dust, tiny grains of carbon, silicates and ice, each smaller than a particle of smoke. This dust absorbs and scatters light, making distant stars appear dimmer and redder. It accumulates in clouds, dark patches against the glow of the Milky Way. These clouds are not empty, they are where stars are born, but they also hide vast regions of the galaxy from view. Much of what we know about the Milky Way comes from infrared or radio observations, wavelengths that can pierce the veil of dust. Dust grains are formed in the atmospheres of dying stars. As stars age and swell into red giants, they shed their outer layers into space. In these cool, dense outflows, atoms can condense into solid grains. Carbon stars produce carbon dust. Oxygen-rich stars produce silicate dust. These grains are then dispersed into the interstellar medium by stellar winds. Over time, they drift through space, accumulating in molecular clouds and eventually incorporating into new stars and planets. The dust in the interstellar medium is recycled material, remnants of stars that died long ago. Some of the dust on Earth, perhaps even some of the dust in your home, may have originated in the atmosphere of a red giant billions of years ago. Infrared telescopes reveal hidden regions. Because dust blocks visible light but allows infrared to pass, infrared telescopes are essential for studying the galaxy's structure. They reveal the galactic center, peer into star-forming clouds, and map the distribution of old, cool stars. Infrared light shows us heat. It reveals places where stars are being born, where planets are forming, and where dying stars shed their outer layers. It is a window into the hidden universe, the parts of the galaxy invisible to our eyes. Infrared astronomy has transformed our understanding of the Milky Way. Before infrared telescopes, the galactic center was a mystery. We knew something massive was there, but we could not see it. Infrared observations revealed the dense concentration of stars surrounding the central black hole. They mapped the bar at the center of the galaxy. They traced the spiral arms through regions obscured by dust. Infrared surveys have catalogued billions of stars, many of which are too cool and faint to be seen in visible light. These surveys have revealed the true extent of the galaxy, its size, its structure, and its complexity. The galaxy emits light across the spectrum. The Milky Way does not shine only in visible light. It glows in radio waves from pulsars and cold gas. It radiates in infrared from dust and cool stars. It flickers in ultraviolet from hot young stars. And it pulses in X-rays and gamma rays from black holes, neutron stars, and supernova remnants. Every wavelength tells a different story. Together, they reveal the full complexity of the galaxy, a spectrum of light spanning from the longest radio waves to the shortest gamma rays. Radio observations reveal the distribution of hydrogen gas. Hydrogen emits a characteristic radio signal at a wavelength of 21 centimeters. By mapping this emission across the sky, astronomers can trace the location and motion of gas throughout the galaxy. They have used this technique to map the spiral arms, to measure the rotation of the disk, and to detect the inflow and outflow of gas. Radio observations also reveal pulsars, compact objects that emit regular pulses of radio waves. These pulsars serve as probes of the interstellar medium. their signals affected by the density of electrons they pass through. Ultraviolet observations reveal hot young stars and regions of intense star formation. X-ray observations reveal hot gas, supernova remnants and accreting black holes. Gamma-ray observations reveal the most energetic processes, pulsar wind nebulae, and possibly dark matter annihilation. Each wavelength adds a layer to our understanding, building a complete picture of the galaxy. Cosmic rays permeate the galaxy. Cosmic rays are not rays at all. They are high-energy particles, mostly protons, racing through space at nearly the speed of light. Some originate from the Sun. Others come from supernova remnants or other violent events. They fill the galaxy, a constant background of invisible radiation. When they strike Earth's atmosphere, they create showers of secondary particles. Cosmic rays are a reminder that space is not empty or calm. It is filled with energy, motion, and danger. Cosmic rays are a puzzle. Despite decades of study, we still do not know exactly where they come from. Supernova remnants are the leading candidate. The shock waves from supernova explosions can accelerate particles to near light speed, but the details are unclear. How does the acceleration work? Can supernovae produce the highest energy cosmic rays, or do those come from somewhere else? Some of the most energetic cosmic rays have energy so high that they should not be able to reach us from distant galaxies. They should lose energy as they travel through space, yet we detect them. This suggests there may be sources of ultra-high energy cosmic rays within our own galaxy or nearby. The search for these sources continues. The galaxy has a magnetic field. The Milky Way is threaded with magnetic fields, weak but vast, stretching across thousands of light years. These fields influence the motion of charged particles, shaping cosmic rays and guiding the flow of ionized gas. They are generated by the movement of plasma in stars and in the interstellar medium. The galactic magnetic field is complex, tangled, and poorly understood, but it plays a crucial role in star formation, in the structure of the disk, and in the behavior of matter on the largest scales. Magnetic fields are difficult to measure. They do not emit light. They cannot be seen directly. Instead, astronomers infer their presence through their effects. Charged particles spiral along magnetic field lines, emitting synchrotron radiation. This radiation is polarized, meaning it oscillates in a preferred direction. By measuring the polarization of light from distant stars or from radio emission, astronomers can map the magnetic field. They have found that the field follows the spiral arms, suggesting it is stretched and amplified by the rotation of the disk. The field is strongest in regions of active star formation, where gas is dense and turbulent. It is weaker in the halo, where gas is sparse. The galactic magnetic field is a hidden structure, an invisible framework shaping the flow of matter and energy. Gas flows into and out of the galaxy. The Milky Way is not a closed system. Gas flows into the disk from the halo, feeding star formation. At the same time, supernovae and stellar winds blow gas outward, creating fountains and bubbles. This cycle, inflow and outflow, regulates how quickly the galaxy forms new stars. Without inflows, the gas would be exhausted. Without outflows, the disk would become too dense. The balance between these processes shapes the galaxy's evolution over billions of years. These flows are called the galactic fountain. Hot gas, heated by supernovae and stellar winds, rises out of the disk. As it rises, it expands and cools. Eventually, it cools enough to condense into clouds. These clouds then fall back into the disk, where they can form new stars. The cycle continues. The fountain helps recycle gas, bringing enriched material back into the disk. It also helps regulate star formation. If star formation becomes too vigorous, the outflows increase, removing gas and slowing down star formation. If star formation slows, the outflows decrease, allowing gas to accumulate and star formation to resume. It is a self-regulating process, a feedback loop that keeps the galaxy in balance. The Fermi bubbles extend above and below the disk. In 2010, astronomers discovered two enormous bubbles of gamma-ray emission extending above and below the galactic center. These Fermi bubbles reach about 25,000 light-years from the disk, symmetric and vast. They are likely the result of past activity from Sagittarius A star, perhaps an ancient outburst of energy or the remnant of a jet. The bubbles are faint and invisible in most wavelengths, but in gamma rays they glow. They are evidence that the galactic center has not always been as quiet as it is today. The origin of the Fermi bubbles is still debated. One possibility is that the central black hole was more active in the past, accreting gas and launching jets of particles outward. These jets would have inflated the bubbles over millions of years. Another possibility is that a burst of star formation in the galactic center produced numerous supernovae whose combined energy drove gas out of the disk and created the bubbles. The bubbles contain high-energy particles, cosmic rays trapped within them. These particles emit gamma rays as they interact with gas and light. The bubbles are slowly expanding, pushing into the halo. They may eventually disperse, but for now, they remain as evidence of a violent past. The Milky Way's rotation curve is flat. When astronomers measure how fast stars orbit at different distances from the galactic center, they find something strange. Stars far from the center move just as fast as those closer in. According to visible matter alone, outer stars should move slower. The fact that they do not suggests there is more mass than we can see. This is one of the strongest pieces of evidence for dark matter. The rotation curve is flat because the galaxy is surrounded by a halo of invisible mass, holding everything together. This observation was one of the first hints that something was missing from our understanding of galaxies. In the 1970s, astronomer Vera Rubin measured the rotation speeds of stars in many galaxies. She found that in almost every case the rotation curve was flat, not declining as expected. At first, this was puzzling, but it led to the realization that galaxies must contain far more mass than we can see. This invisible mass is dark matter. Its presence shapes the rotation of galaxies, the motion of galaxy clusters, and the structure of the entire universe. Without dark matter, galaxies as we know them could not exist. Dark matter halos surround galaxies. The Milky Way is embedded in a massive halo of dark matter extending far beyond the visible disk. This halo contains several times more mass than all the stars and gas combined. Its gravity shapes the galaxy's rotation, its structure, and its ability to capture satellites. We do not know what dark matter is made of. It does not interact with light. It does not collide with itself in any way we can detect. Yet it dominates the universe, invisible architecture holding galaxies together. Computer simulations suggest that dark matter halos are not smooth. They are filled with substructure, clumps and streams of dark matter left over from past mergers. Some of these clumps may still exist today, orbiting within the halo. If so, they could be detected through their gravitational effects on stars. Astronomers are searching for these dark matter clumps, hoping to learn more about the properties of dark matter. The halo is also thought to be roughly spherical, much larger than the disk. It extends for hundreds of thousands of light years, perhaps even farther. The exact size is uncertain. The halo fades gradually into the surrounding intergalactic space with no clear boundary. The local bubble is a cavity in the interstellar medium. The Sun lies within a region called the local bubble, a cavity about 1,000 light-years across carved out by ancient supernova explosions. Within this bubble, the gas is hotter and thinner than average. The bubble's walls are denser, marked by clouds and new star formation. We are floating in a quiet, cleared-out region shaped by stars that died millions of years ago. It is a reminder that the space around us, though it seems empty, has structure and history. The local bubble was created by a series of supernovae that occurred roughly 10 to 20 million years ago. These explosions were likely from a group of massive stars that formed together and died in quick succession. Their combined energy swept out a cavity in the interstellar medium, pushing gas and dust to the edges. The interior was left hot and nearly empty. The Sun entered this bubble relatively recently, perhaps within the last 5 million years. Before that, it was likely in a denser region, possibly within a molecular cloud. The local bubble is not unique. The galaxy is filled with similar bubbles and cavities, each carved by past supernova explosions. The solar system's location is called the Orion Spur. We do not live in one of the Milky Way's major spiral arms. Instead, the solar system resides in a smaller feature called the Orion Spur, or local arm, a minor branch between the Sagittarius and Perseus arms. It is a relatively quiet region, sparse and peaceful. We are about 26,000 light-years from the galactic center, roughly halfway out from the core to the edge of the disk. It is a good place to be, neither too crowded nor too isolated. The Orion Spur is a small connecting arm, sometimes called a bridge between the larger spiral arms. It is less dense, less active, and less prone to the violent events that occur in the major arms. This relative calm may have been important for the development of life on Earth. In denser regions, supernova explosions are more frequent. Gamma-ray bursts, intense pulses of radiation from collapsing stars, are more common. Encounters with molecular clouds are more frequent. All of these could disrupt planetary systems or harm life. The Orion Spur is a safe haven, a quiet neighborhood where life can flourish undisturbed. The nearest star to the Sun is Proxima Centauri. Just over 4 light-years away, Proxima Centauri is the closest star to our solar system. It is a small red dwarf, faint and cool, invisible to the naked eye. It is part of a triple star system, orbiting 2 brighter stars, Alpha Centauri A and B. Proxima has at least one known planet, Proxima b, which orbits in the star's habitable zone. It is the nearest exoplanet we know of, a reminder that even our closest neighbours may harbour worlds. Proxima b orbits its star every 11 days. It is slightly more massive than Earth and lies at a distance where liquid water could exist on its surface. However, Proxima Centauri is a flare star. It regularly emits powerful flares, bursts of radiation that could strip away any atmosphere on the planet. Whether Proxima b is habitable is uncertain. It depends on whether it has a magnetic field strong enough to protect it from the flares and whether it has retained an atmosphere. Even if Proxima b is not habitable, the discovery suggests that planets are common, even around small, faint stars like red dwarfs. There are hundreds of billions of stars in the Milky Way. Estimates vary, but most astronomers agree the Milky Way contains between 100 billion and 400 billion stars. The exact number is hard to pin down. Many stars are too faint to detect, others are hidden behind dust. But the galaxy is vast, and every patch of sky, if observed closely enough, reveals more stars. Among those billions, some are newborns, some are ancient, and some, perhaps, are orbited by planets where life has emerged. Think about what this means. If even a tiny fraction of stars have planets, and an even tinier fraction of those planets are habitable, there could still be millions or billions of potentially habitable worlds in the Milky Way alone. The question is not whether other worlds exist. They do. The question is whether any of them harbour life, and if they do, whether that life is simple microbes or complex civilizations. We do not know. But the sheer number of stars suggests that the galaxy is filled with possibilities, countless worlds waiting to be discovered. The Milky Way is part of the local group. The Milky Way does not float alone. It is part of a collection of galaxies called the local group, a loose cluster bound by gravity. The group contains over 80 galaxies, though most are small dwarfs. The three largest members are the Milky Way, Andromeda, and Triangulum. Together, these galaxies orbit their common center of mass, a slow gravitational dance that will eventually bring them closer. The local group is just one small corner of a much larger cosmic web. The local group is roughly 10 million light-years across. Most of its members are dwarf galaxies, small, faint, and difficult to detect. Some orbit the Milky Way or Andromeda as satellites. Others drift independently, held loosely by the group's collective gravity. The local group is itself part of a larger structure moving toward the Virgo cluster, pulled by its immense gravity. On the larger scales, galaxies are not randomly distributed. They form groups, clusters, and superclusters, connected by filaments of dark matter and gas. The local group is a single node in this vast cosmic web. The Virgo supercluster contains the local group. The local group, in turn, is part of a much larger structure, the Virgo supercluster, a vast collection of galaxy groups and clusters stretching over 100 million light-years. At the heart of this supercluster lies the Virgo cluster, a dense concentration of thousands of galaxies. The Milky Way and its neighbours are falling toward the Virgo cluster, pulled by its immense gravity. But even this supercluster is not the end. It is part of Laniakea, an even larger structure, a current in the cosmic web. Laniakea is a supercluster of superclusters. It contains roughly 100,000 galaxies, spanning over 500 million light-years. The name means immeasurable heaven in Hawaiian. Laniakea is defined not by boundaries but by motion. Galaxies within Laniakea are all flowing toward a common center of mass, the Great Attractor. Beyond Laniakea lie other superclusters, Perseus, Pisces, Coma, Shapley. Together, they form the cosmic web, a vast network of filaments and voids that spans the observable universe. The Milky Way is part of this web, one galaxy among billions, caught in the slow currents of gravity that shape the largest structures in existence. The galaxy is moving through space. The Milky Way is not stationary. It is moving through space at over 600 kilometers per second, relative to the cosmic microwave background. This motion is the result of gravitational pulls from surrounding structures, the attraction of the Virgo cluster, the Great Attractor, and other massive concentrations of matter. We orbit within a galaxy. The galaxy moves within a cluster, and the cluster itself drifts through the universe. Motion is built upon motion, scales upon scales. The cosmic microwave background is the faint afterglow of the Big Bang, radiation that fills the entire universe. It is almost perfectly uniform, the same temperature in all directions. But there is a slight asymmetry. The radiation is slightly hotter in one direction and slightly cooler in the opposite direction. This asymmetry is caused by our motion through space. As we move toward the hot spot, the radiation is blue shifted. As we move away from the cold spot, it is red shifted. By measuring this asymmetry, astronomers can determine our velocity relative to the cosmic microwave background. This is called our peculiar velocity, the motion of the Milky Way relative to the expansion of the universe. The Great Attractor pulls nearby galaxies. Somewhere beyond the disk, hidden by the zone of avoidance, lies a massive concentration of mass called the Great Attractor. It exerts a gravitational pull on the Milky Way and thousands of other galaxies in the local region. We are all falling toward it, but we cannot see it directly. It lies behind the galactic plane, obscured by dust and stars. We know it exists only by observing the motion of galaxies around it, a hidden giant pulling strings across hundreds of millions of light-years. The Great Attractor is not a single object. It is a region of space containing many galaxy clusters bound together by gravity. The largest of these is the Norma cluster, a massive concentration of galaxies lying roughly 200 million light-years away. But the Great Attractor may be just part of an even larger structure, the Shapley supercluster, one of the most massive structures in the nearby universe. The exact nature of the Great Attractor is still debated. What is clear is that it exerts a powerful influence on the motion of galaxies, including our own. The zone of avoidance blocks our view. Because we live within the Milky Way's disk, the disk itself blocks our view of much of the universe. This region, called the zone of avoidance, spans about 20% of the sky. Within this zone, dust and stars obscure distant galaxies, making it difficult to map the large-scale structure of the universe. Astronomers must rely on radio and infrared observations or look around the zone to piece together what lies beyond. The galaxy is both our home and our blindfold. The zone of avoidance is frustrating for astronomers. It hides vast regions of the universe, including potentially important structures. Recent surveys using infrared and radio telescopes have begun to penetrate the zone, revealing previously unknown galaxies and clusters. These discoveries are filling in the gaps in our map of the universe, but the zone remains a challenge. It is a reminder that our view of the cosmos is limited by our location, trapped within a dusty disk, looking out through a foggy window. The Milky Way will remain visible for billions of years. For now, the night sky is filled with stars. But galaxies are not eternal in their current forms. In billions of years, as the Milky Way and Andromeda merge, the night sky will change. New constellations will form. The galactic disk may thicken or dissolve, star formation may surge, then fade. But the stars themselves will remain, scattered through a larger, older galaxy. Future beings, if they exist, will look up and see a different sky, but they will still be home. Eventually, in the very distant future, trillions of years from now, star formation will cease. The gas will be exhausted, no new stars will be born. The existing stars will gradually burn out, one by one. The galaxy will grow darker, dimmer, quieter. White dwarfs will cool to black dwarfs. Neutron stars will slowly fade. Black holes will evaporate through Hawking radiation, an unimaginably slow process. In the end, the galaxy will be a dark, cold relic, a faint ghost of what it once was. But that end is so far in the future that it is almost meaningless to consider. For now, the galaxy is alive, vibrant, filled with light and motion. The Milky Way has inspired humanity for millennia. Long before we understood what the Milky Way was, humans looked up and wondered. Ancient cultures saw it as a river, a path, a bridge between worlds. The Greeks called it the milk of Hera. The Chinese saw it as a silver stream. It has guided travelers, inspired myths, and sparked questions about our place in the cosmos. Even now, when we understand it is a galaxy, a spiral of stars turning through space, it still fills us with awe. It connects us to the past and the future, to the Earth and the stars. Different cultures have told different stories about the Milky Way. In some myths, it is a road to the afterlife, a path for souls to travel. In others, it is a river of stars, a bridge between heaven and earth. The Milky Way has been a source of wonder and mystery, a reminder of the vastness beyond our small world. Today, we know it is not a myth, but a galaxy. Yet the wonder remains. We are part of this galaxy. We are made from its matter. We are kin to its stars. Some stars in the Milky Way have planets. Over the past few decades, astronomers have discovered thousands of exoplanets, worlds orbiting other stars. Some are gas giants, larger than Jupiter. Others are rocky, similar to Earth. A few lie in the habitable zone, where liquid water could exist. The Milky Way is not just a collection of stars. It is a collection of planetary systems, a galaxy of worlds. Among those billions of planets, it is possible, perhaps even likely, that some harbour life. Exoplanet discoveries have revolutionized our understanding. Before the first exoplanet was confirmed in the 1990s, we did not know if planets were common or rare. Now we know they are ubiquitous. Nearly every star has at least one planet, some have many. Planetary systems come in all varieties: hot Jupiters orbiting close to their stars, super-Earths larger than our own, mini Neptunes with thick atmospheres. The diversity is staggering. Among this diversity, some planets resemble Earth, rocky worlds orbiting in the habitable zone where temperatures allow liquid water. These are the most tantalizing targets in the search for life. We do not know if we are alone. Despite decades of searching, we have found no definitive evidence of life beyond Earth. No signals, no structures, no signs of intelligence. The galaxy is vast, and we have only just begun to look. Perhaps life is rare. Perhaps it is common but quiet. Perhaps we are listening in the wrong way, or looking in the wrong places. Or perhaps someday soon we will detect a signal, a message from across the stars, and realize we were never alone. The search for extraterrestrial intelligence continues. Radio telescopes scan the sky, listening for artificial signals. Optical telescopes search for laser pulses. Astronomers analyze the light from exoplanets, looking for signs of life in their atmospheres. So far, the search has been unsuccessful. But the universe is vast, and our efforts are still in their infancy. The absence of evidence is not evidence of absence. The galaxy could be teeming with life, and we might simply not have found it yet. Or we could be alone, a rare experiment in a vast, empty cosmos. Both possibilities are profound. The galaxy is older than most of its stars. Though the Milky Way formed over 13 billion years ago, most of its stars are much younger. Star formation is an ongoing process. New stars are born, old stars die, and the cycle continues. The galaxy's oldest stars are rare, scattered through the halo. The disk is filled with younger generations, stars that have formed over billions of years from gas enriched by their predecessors. The galaxy is both ancient and constantly renewing. This means the galaxy has a history. It began as a small, irregular collection of gas and dark matter. Over time, it grew through mergers and accretion. The first stars formed from pristine gas, pure hydrogen and helium. These stars lived and died, enriching the gas with heavier elements. Subsequent generations of stars inherited this enriched gas, incorporating carbon, oxygen, and iron into their composition. The process continued, generation after generation, each adding to the galaxy's chemical wealth. The Sun is a late-generation star, born from gas already enriched by countless earlier generations. The planets, including Earth, are made from the remnants of those earlier stars. Some regions of the galaxy are more active than others. Star formation is not evenly distributed. It concentrates in spiral arms, in molecular clouds, in regions where gas is dense and cool. Other parts of the galaxy are quiet, nearly empty, with little gas and few new stars. The galactic center is crowded, but star formation is limited there. The halo is sparse and old. The disk is active but uneven. The galaxy is a patchwork, some regions bustling with birth, others silent and still. The most active regions are the giant molecular clouds. These are the largest structures in the galaxy, clouds of gas and dust stretching across hundreds of light years. Within them, star formation proceeds at a rapid pace. Thousands of stars may be born in a single cloud over a few million years. The most massive stars form in the densest cores, while lower mass stars form in the outskirts. The cloud is gradually consumed. Gas is converted into stars. Stellar winds and supernova explosions disperse the remaining gas. Eventually, the cloud is destroyed, leaving behind a star cluster. The cycle then repeats elsewhere in other clouds, other regions of the galaxy. The Milky Way's future is tied to Andromeda. In 4.5 billion years, when the Milky Way and Andromeda collide, everything will change. The merger will trigger bursts of star formation as gas clouds collide and compress. The supermassive black holes at each galaxy's center will spiral together, eventually merging into a single, larger black hole. The resulting galaxy, sometimes called Milkomeda, will be larger, older, and elliptical rather than spiral. It will be a new galaxy, born from the union of two, the next chapter in a story that began billions of years ago. Milkomeda will be different from either parent galaxy. It will have no spiral arms, no disk. Just a smooth, featureless ellipsoid filled with old, red stars. Star formation will have ceased. The gas will have been consumed or expelled. The galaxy will be quiet, stable, aging gracefully over trillions of years. It will orbit within the local group, along with any remaining dwarf galaxies. Eventually, in the far future, it may merge with other members of the group, growing even larger. But by then, the universe will be very old, very empty, and very dark. Stars will survive the merger. During the collision, individual stars will almost never hit each other. The distances between stars are so vast that even during a galactic merger, they pass by like ships in the night. Some will be flung into new orbits, others will remain relatively undisturbed. The Sun, if it still exists, may find itself in a different part of the merged galaxy, but it will not be destroyed. The merger will be chaotic on galactic scales, but peaceful on the scale of individual stars. The Sun will likely survive long enough to witness the merger, but it will be near the end of its life. In about 5 billion years, the Sun will swell into a red giant, expanding to engulf the inner planets. Earth may be consumed, or it may survive as a scorched, lifeless rock orbiting a dying star. By the time the merger occurs, the Sun will be a white dwarf, a fading ember. From its vantage point, if any observers remain, they would see the two galaxies slowly intertwining, a cosmic dance unfolding over hundreds of millions of years. The Milky Way's disk may dissolve. Spiral galaxies like the Milky Way are young and dynamic, their disks shaped by rotation. But when two spirals merge, the result is often an elliptical galaxy, older and more stable. The disk may thicken, lose its structure, or dissolve entirely. The stars will remain, but their orbits will become random rather than organized. The elegant spiral will give way to a smooth, featureless ellipsoid. It will be a galaxy shaped by gravity and time, not by rotation. Elliptical galaxies are the end state of galaxy evolution. They form from mergers when two or more spirals collide and mix. The ordered rotation of the disks is lost. The stars are scattered into random orbits. The result is a smooth, round, or elliptical galaxy. Ellipticals contain mostly old stars. They have little gas and little star formation. They are quiet, stable, and long-lived. In the distant future, most galaxies in the universe will likely be ellipticals. The spirals we see today are a phase, a temporary stage in the long evolution of galaxies. Some stars will be ejected from the galaxy. During the merger, gravitational interactions will be violent. Some stars, especially those in the outer regions, may be flung out of the galaxy entirely, sent tumbling into intergalactic space. These stars will wander alone, far from any galaxy, isolated in the dark. They are not destroyed, merely exiled. They will continue to shine, but they will no longer belong to any structure, wanderers in the void between galaxies. These ejected stars are called intergalactic stars. They drift through the space between galaxies, unbound by any gravitational structure. They are isolated, lonely, far from any companions. If planets orbit these stars, the night sky from those planets would be nearly empty. No Milky Way arching overhead, no neighbouring stars, just a vast, empty blackness punctuated by a few distant galaxies. It would be a lonely existence, adrift in the cosmic void. New stars will form during the collision. Though the merger will be chaotic, it will also trigger intense star formation. As gas clouds collide, they compress and new stars ignite. For a time, the merging galaxies will glow brightly, filled with young, hot stars. This starburst phase may last for hundreds of millions of years. Then, as the gas is exhausted, star formation will slow, the galaxy will age, settle, and quiet. But for a brief period, it will burn brightly, a final flourish before stillness. Starburst galaxies are among the brightest objects in the universe. They form stars at rates hundreds of times faster than the Milky Way. Their intense radiation can be detected across vast distances. They are often the result of mergers or close encounters, events that compress gas and trigger bursts of star formation. The Milky Way Andromeda merger will likely produce a starburst, lighting up the local group for a few 100 million years. Then the burst will fade and the galaxy will settle into old age. The Milky Way is shaped by gravity and time. Every feature of the galaxy, from its spiral arms to its warp, from its globular clusters to its stellar streams, is the result of gravity acting over billions of years. Gravity pulls gas into clouds. It collapses clouds into stars. It binds stars into clusters and clusters into galaxies. It tears apart smaller galaxies and stitches their remnants into larger ones. Gravity is the sculptor and time is the medium. Together, they have shaped the Milky Way into what it is today. Gravity is the fundamental force shaping the universe. It is the weakest of the four fundamental forces, but it acts over the largest scales. It binds atoms into molecules, molecules into planets, planets into stars, stars into galaxies, and galaxies into clusters. It shapes the structure of the universe, creating the cosmic web of filaments and voids. Gravity never stops. It never tires. It acts continuously, patiently, pulling matter together, building structures, shaping the cosmos. The Milky Way is constantly evolving. Though the galaxy seems stable on human timescales, it is always changing. Stars are born and die, gas flows in and out. Satellites are consumed, the disk warps and settles, the arms shift, the black hole feeds. Over millions and billions of years, the galaxy transforms, growing, aging, evolving. It is not a static object. It is a process, a structure in motion, a story unfolding across time. This evolution is driven by many processes. Star formation converts gas into stars. Supernovae return enriched gas to the interstellar medium. Accretion brings in new material from the halo and from satellite galaxies. Mergers add mass and reshape the structure. Dynamical friction causes orbiting satellites to slow and spiral inward. Tidal forces stretch and tear apart smaller galaxies. All these processes are ongoing, constantly reshaping the galaxy. The Milky Way we see today is a snapshot, a single frame in a long, slow movie. The galaxy is home to countless phenomena. Within the Milky Way, nearly every cosmic event we can imagine is happening somewhere. Right now, stars are exploding, planets are forming, black holes are devouring matter, pulsars are spinning, binary stars are stealing gas, nebulae are glowing, cosmic rays are racing through space. The galaxy is not a quiet backdrop. It is a theatre of constant activity. a stage where the universe plays out its drama on scales both vast and intimate. Think of the sheer variety of events occurring at this very moment. Somewhere, a star is being born, its core heating up until fusion ignites. Somewhere else, a massive star is reaching the end of its life, its core collapsing, about to explode. A neutron star is spinning hundreds of times per second, its beams sweeping across space. A black hole is tearing apart a star that wandered too close, flinging half the star's mass into space while consuming the rest. A planetary system is forming, dust grains colliding and sticking together, gradually building up planets. The galaxy is alive with activity, a cosmic symphony playing out across space and time. The Milky Way is beautiful. Beyond the science, beyond the data, there is something else. Beauty. The way starlight curves along the disk, the glow of nebulae, the dark silhouettes of dust, the spiral arms sweeping outward, the faint halo surrounding it all. The Milky Way is not just a collection of matter. It is a structure of elegance, a pattern woven from light and gravity, motion and time. It is beautiful in a way that transcends understanding, a reminder that the universe is not just knowable, but also wondrous. This beauty is not accidental. It arises from the laws of physics, from the interplay of gravity and motion, from the behavior of gas and dust. The spiral arms form because of density waves. The halo glows with the light of ancient stars. The disk is flat because of rotation. Each feature has a cause, a reason, yet the whole is greater than the sum of its parts. The galaxy is beautiful not despite the physics, but because of it. The same laws that govern atoms govern galaxies. The same forces that hold molecules together hold stars in orbit. Beauty and science are not separate. They are two ways of seeing the same thing. We are part of the galaxy. It is easy to think of the Milky Way as something distant, something out there. But we are not separate from it. We live within it. Every atom in our bodies came from the galaxy. The oxygen we breathe, the carbon in our cells, the calcium in our bones, all of it was forged in stars. We are made of the same matter that makes the galaxy. We are not observers, we are participants. The galaxy is not just our home, it is us. This connection is profound. We are made of star stuff, as Carl Sagan famously said. The iron in our blood was forged in a supernova. The calcium in our bones was created in a dying star. The water in our bodies contains hydrogen from the Big Bang and oxygen from stellar cores. We are walking collections of atoms that have travelled through space and time, cycling through stars, through clouds, through planets, and now through us. When we look up at the Milky Way, we are looking at our origins, our history, our kin. Some stars are moving faster than expected. Among the stars in the galaxy, a few are moving faster than they should. These runaway stars were likely ejected from binary systems or clusters, flung out by gravitational interactions or supernova kicks. They raced through space, sometimes fast enough to escape the galaxy entirely. Their high speeds make them outliers, exceptions to the slow, steady orbits most stars follow. But they remind us that the galaxy is not entirely predictable, that even within its order there is chaos. Runaway stars can be identified by their high velocities. They move faster than the typical orbital speed for stars at their location. Some were ejected from the galactic center, flung out by interactions with the supermassive black hole. Others were kicked out of star clusters by gravitational encounters. Still others were companions to stars that exploded as supernovae. When a star explodes, it can give its companion a sudden kick, sending it flying through space. Runaway stars are reminders that violence is part of the galaxy's history, that order and chaos coexist. Brown dwarfs are failed stars. Not every collapsing cloud becomes a star. Some do not gather enough mass to ignite fusion in their cores. These are brown dwarfs, objects too large to be planets but too small to be stars. They glow faintly with leftover heat from their formation, slowly cooling over billions of years. Brown dwarfs are common but difficult to detect. They drift through the galaxy, dark and silent, occupying the space between planets and stars. Brown dwarfs are sometimes called substellar objects. They occupy a middle ground between stars and planets. The dividing line is roughly 13 times the mass of Jupiter. Below this mass, the object is a planet. Above it, the core becomes hot enough to fuse deuterium, a heavy isotope of hydrogen. This limited fusion is not enough to sustain the object like a true star. The brown dwarf glows faintly for a while, then cools. They may be as common as stars hidden in the darkness. Some stars rotate incredibly fast. Most stars rotate slowly, taking weeks or months to complete a single spin. But some rotate at extreme speeds, their surfaces moving at hundreds of kilometers per second. These rapid rotators are often young, massive, and still contracting. Their fast spin affects their shape, flattening them at the poles. It influences their magnetic fields and their stellar winds. A few reach such high speeds that they fling off material, forming glowing disks around themselves. The Sun rotates once every 25 to 35 days, depending on latitude, but these fast spinning stars rotate hundreds of times more quickly, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the dark. Fast rotation changes everything about a star. It flattens the star, making it oblate rather than spherical. The poles are closer to the center than the equator. This distortion affects the star's structure, its temperature distribution, and its evolution. Fast rotation also generates strong magnetic fields. These fields can launch stellar winds, streams of charged particles flowing outward. They can produce flares, sudden bursts of energy that light up the star. Fast rotating stars are dynamic, active, unpredictable. They are the thrill seekers of the galaxy. The galaxy is tilted relative to the ecliptic. From Earth, the Milky Way arcs across the night sky in a graceful band of light, but it does not align with the plane of our solar system. The galactic plane, the flat disk in which most of the galaxy's stars reside, is tilted about 60 degrees relative to the ecliptic, the path traced by the Sun and planets. This tilt is why the Milky Way rises at an angle and why it shifts position with the seasons. We are part of the galaxy, but our own little system is angled slightly askew. A small tilted boat drifting through a larger spinning sea of stars. This tilt is thought to be the result of the solar system's formation. The molecular cloud from which the Sun formed was oriented at an angle relative to the galactic plane. As the cloud collapsed, it preserved this orientation. The disk of material that formed around the young Sun, from which the planets eventually formed, inherited this tilt. Now, billions of years later, the ecliptic remains tilted relative to the galactic plane. It is a fossil, a remnant of the cloud's original orientation, a reminder that the solar system formed from a small, chaotic piece of the galaxy. Some stellar remnants are older than the galaxy's disk. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled. Their existence hints at an earlier time of star formation, a deeper history etched into the outer halo. They have burned for billions of years, slowly fading, carrying with them the quiet residue of a time when the Milky Way was still gathering its shape. The disk may be bright, but the halo remembers further back. These ancient white dwarfs are among the oldest objects in the galaxy. They are the remnants of stars that formed over 12 billion years ago, in the first billion years of the galaxy's existence. At that time, the Milky Way was still assembling, still gathering mass from the surrounding dark matter halo. The disk had not yet formed. Star formation occurred in small, scattered clumps, the proto-galaxy slowly growing. The stars that formed then have long since died, leaving behind white dwarfs that still glow faintly, cooling embers of the first generation. The farthest stars orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light years from the center. These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant sentinels. They are faint, sparse, and far between, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not just what we see. It extends deep into the dark, shaped by wanderers at its edge. These outermost stars mark the edge of the Milky Way's gravitational influence. Beyond them, the galaxy's gravity fades and intergalactic space begins. But even these distant stars are bound to the galaxy. They move slowly, their orbits taking so long that they have completed only a handful of circuits since the galaxy formed. They are the galaxy's frontier, the boundary between the Milky Way and the void beyond. The Milky Way's shape is lopsided in several ways. Though often pictured as a symmetric spiral, the Milky Way is subtly lopsided. One side of the disk is thicker than the other. The spiral arms are uneven in brightness and extent. Even the stellar halo is slightly off-center. These asymmetries likely arise from gravitational interactions with the Magellanic Clouds, with dark matter clumps, or with past mergers. The galaxy is not a perfect pinwheel. It is a living structure marked by tugs and twists, like a spinning dancer whose skirt has been caught by the wind. Its beauty lies in that irregularity, a graceful imbalance sculpted by time. Asymmetries are common in galaxies. Perfectly symmetric spirals are rare. Most galaxies show lopsidedness, warps, or other irregularities. These features are clues to the galaxy's history and environment. They reveal past interactions, ongoing disturbances, and the influence of invisible dark matter. The Milky Way's asymmetries tell us it is not isolated. It is part of a larger system, interacting with neighbours shaped by forces both seen and unseen. Astronomers map the galaxy using variable stars. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow luminous heartbeats. These are variable stars, and some types, like Cepheids and RR Lyrae, have well-known relationships between their brightness and their pulse period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity, and by comparing that to how bright it appears, its distance. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the dark, blinking beacons scattered through the spiral. Cepheid variables are especially useful. They are bright, making them visible over large distances. Their period-luminosity relationship is tight and well calibrated. By measuring the period, astronomers can determine the star's intrinsic brightness. Comparing this to the observed brightness gives the distance. This method was used by Henrietta Leavitt in the early 20th century to measure distances to nearby galaxies, revealing for the first time that the universe extends far beyond the Milky Way. Cepheids remain a cornerstone of the cosmic distance ladder, the series of methods used to measure distances across the universe. The Gaia mission is revolutionizing our understanding of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever made. By measuring the positions, motions, and brightness of over 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and its motion through time. It has uncovered streams from shredded galaxies, mapped the warp of the disk, and traced the Sun's orbit with exquisite detail. With each new data release, Gaia deepens our understanding, turning a hazy smear of stars into a sharp, living map. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars. Gaia's precision is staggering. It measures stellar positions to within a few millionths of an arcsecond. This is equivalent to measuring the width of a human hair from 1,000 kilometers away. With such precision, Gaia can detect the motion of stars across the sky, revealing not just their positions but their velocities. This data allows astronomers to trace orbits, identify streams, and reconstruct the history of the galaxy. Gaia is not just mapping where stars are. It is mapping where they have been and where they are going. The galactic plane marks a dense path of stars. If you look up on a dark night away from city lights, you may see a hazy river of starlight crossing the sky. That is the galactic plane, the thickest slice of the Milky Way's disk. It is not a line, but a depth, a vast flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point, we are looking along the grain of the galaxy, peering through its richest corridors. This band is not just beautiful. It is the crowded, humming heart of where most stars live and die. The galactic plane is where the action is. Most star formation occurs here. Most supernovae explode here. Most of the galaxy's mass resides here. When we look along the plane, we are looking through the galaxy's thickest regions. Billions of stars lie along that line of sight, their light blending into a soft glow. It is humbling to realize that each faint patch of light contains countless individual stars, each with its own story, its own history, its own future. The night sky is brightest toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich, glowing concentration of stars, dust, and unseen mass. From Earth, we cannot see the very center in visible light. Dust clouds obscure our view, but the area glows with brightness in infrared and radio. Even with the naked eye, the region appears more crowded, more luminous, filled with the overlapping light of billions of stars. We orbit far from this center, in a quiet suburb of the galactic disk. But when we look inward, we glimpse the crowded city at the galaxy's heart. On a dark night, far from light pollution, the region towards Sagittarius is stunning. The Milky Way thickens and brightens. Dark dust lanes weave through the glow. Nebulae glow faintly, splashes of colour against the pale band. It is a view that has inspired humanity for thousands of years. Ancient peoples wove stories around this band of light. Modern astronomers study it with telescopes and instruments, but the sense of wonder remains the same. We are looking into the heart of our home, the center of the galaxy, the place where it all began. We see the Milky Way edge on from Earth. Because we live within it, we cannot look down on the Milky Way from above. Instead, we see it from the inside, a flat ribbon of stars stretching across the sky, curved only by the horizon. This edge-on view compresses the galaxy into a single arc, making it hard to grasp its full structure from our perspective. It took centuries of observation, cataloguing, and mathematical reasoning to realize the spiral we belong to. From Earth, we gaze through its disk, like standing in a forest and looking along the line of the trees. We do not see the shape we are part of, only the vastness that surrounds us. Understanding the Milky Way's structure required painstaking work. Early astronomers counted stars, measured their positions, and mapped their motions. William Herschel, in the late 18th century, tried to map the galaxy by counting stars in different directions. He concluded, incorrectly, that the Sun was near the centre. It was not until the early 20th century, with the work of Harlow Shapley and others, that we realised the Sun is far from the galactic centre. Shapley studied globular clusters, mapping their distribution and realising they were centred on a distant point. That point was the true centre of the galaxy. We were not at the centre. We were in the suburbs, a humbling realisation. The galaxy holds far more than we can ever possibly see. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in silence. Dark matter outnumbers luminous stars. Between every star lies emptiness, and within every empty space, potential. The Milky Way is not just what we see. It is what we suspect, what we infer, what we long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. And within that vastness, somehow we find ourselves. One planet among many, orbiting a quiet star, floating through a story too wide for the eye. There is so much we do not know. What is dark matter? How common is life? Are we alone? What happens inside a black hole? How will the galaxy evolve in the distant future? These questions remain open, but that is part of the beauty. The Milky Way is not a finished story. It is an ongoing investigation, a mystery we are slowly unraveling. Each discovery brings new questions. Each answer reveals deeper complexity. The galaxy is a gift, an infinite source of wonder, a reminder that the universe is vast and we have only begun to explore it. And now the stars begin to dim behind your thoughts. We have drifted through 100 quiet truths. From the warp of the galaxy's disk to the farthest halo stars, from newborn suns to long-dead remnants, from dust and gas to light and shadow and everything in between. You have wandered through stellar nurseries, danced along spiral arms and gazed toward the galactic heart glowing behind curtains of dust. You are a part of this galaxy, not just a passenger on Earth, but a participant in its long and luminous unfolding. The iron in your blood was forged in stars. The oxygen you breathe was sculpted in ancient explosions. The atoms of your body traced their lineage to the earliest times, born from the same matter that now fuels suns and whispers through clouds of interstellar dust. Tonight, as you rest, the galaxy turns on. Stars are forming. Light is travelling. Silent orbits continue, and you are floating within it. A small warmth in the dark, resting in the spiral arm of a quiet, radiant sea. If you happen to still be awake, you can go ahead and watch the next chapter now. I hope you sleep well and dream softly. Good night.